Hi everyone, this video is going to cover some concentricity examples, two specific examples that pop up a lot. The idea or goal is to show you the pitfalls or problems you can come across when measuring concentricity in Aberlink3D, why they occur, and little fixes on how to get better results when setting up your parts or getting your measurements. Before we get started, I think it's good to cover some basic examples of where concentricity is easily measured and easily applied. So Aberlink3D treats concentricity as a 2D size, meaning it can only be dimensioned between circles, and those circles have to be projected into a plane. The idea then being the position will be verified from one circle to the other. Now, as standard, this is normally applied on things like bearings. So this is a good example, where basically the two circles that are being checked to each other are measured or projected at the same height. So you can imagine with this bearing, we'd have a plane, we then measure the internal circle, then the external circle, and the measurements would be taken at pretty much the same height. So there's no height differential that is going to cause the measurement to be skewed. The same with the plane, so they'd both be projected into the same plane, meaning there's no skewing of measurements from one plane to the next. Another good example is, this is one of our air bearings, and the idea is, we need to verify that the central hole for the spring lines up with the O-ring seal, and if you can imagine, they would both be measured from this face around about 1 millimeter down. So they're both being measured at the exact same height, meaning there's no skewing or axis line skewing occurring on the part, which is going to give us a varied measurement depending on the height that we measure it at. Okay, so with that being said, I think we should now go on to the two examples that normally cause people problems. Before we begin, I'd just like to highlight the fact that concentricity has actually been eliminated from the latest ASME standard. That's the 2018 standard. But even in previous versions, it was recommended to use runout or position controls instead of concentricity wherever possible. Hopefully you'll see why it is such a headache and such a ambiguous, confusing control to apply to measurements in the next two examples. But yeah, it's worth noting it has actually been dropped from the latest standard. And this document, just to reference it, is from the gd&t basics.com website. There's also a lot of other useful stuff on there, so shout out to them. But let's move on to the next examples. So this example, we have essentially the two parts on the machine. One is completely nominal, and one we have the block has been machined fine, but the bore on the back has been put in with a 5-degree axis tilt. So perfect example, where you basically want to check the back bore to the front bore. So we've got a 20 micron concentricity check from the back bore to the front bore, which is datum A. And in reality, the bore's been put in on a 5-degree tilt. So let's open up Aberlink, and we will program this from CAD just to show you the nominal data and see the variances you can get depending on the setup and the application. So this is the first example. And this is a program that has been created from the CAD, so it's exactly as it is on the drawing you just looked at. And you can see the software is behaving as we would expect. So the nominal model, or the nominal feature, we have the datum bore on the front, so that is a circle projected into the front plane. And then we're doing a concentricity check on the back circle projected into the back plane. And because it's all perfectly aligned up and perfectly square and parallel, we get 0 positional error, which results in a 0 concentricity error. When we look over to the actual data, so this is the bore with the 5-degree tilt on. You see we have the datum B bore, same thing, a circle in a plane in the front face, and then the circle and plane on the back face. This, because it's skewed, it produces a high concentricity error, and that is displayed here by the X error that is occurring, and it results in a 0.524 concentricity error. This is before we even actually measure anything on the CMM, so this is just from the nominal CAD data. Now, This is all working well, but the dilemma we have whenever there is a axis tilt, which is what we're trying to check, is that the depth in which we measure the circle on this bore will have a massive effect on the concentricity, because as we go deeper and deeper into this bore, the projection of the circle will shift along to the right, and it gets worse and worse and worse. So what you're going to have is a situation in which if you run this program multiple times, but the circle is measured at different depths, you will end up with different concentricity values. This is completely normal, and it's one of the reasons why concentricity is a bad callout, and why runout is preferred, as it checks the entire feature as well as the outside profile of the cylinder. But just to highlight the issue, if we go to layers and switch on the offset planes, which I created earlier, you can hopefully see here, as we go deeper into the feature, so all I've done is offset planes from the initial front face, but the projection of the circles has been done at set depths. So at -5, we end up with a 0.929 concentricity callout, or error, sorry. At -10, it goes to 1.67. And at -15 we end up at 2.595. So hopefully this highlights why you can sometimes see big issues whenever there's a change in axis travel when doing concentricity checks. And this is example 1. There are other issues which we are going to highlight in example 2, but hopefully this gives you an insight into why you can see different concentricity errors depending on the depth in which you measure the circle. This is example 2, and as you can see in this example, I'm going to highlight the issue with circle projections, as they use the circles have to be projected into a plane, and if the plane isn't perfectly square, it will skew the position and form of the circle. So in this example, both the nominal and the actual have perfectly aligned through bores, but you'll see that the software skews the readings because of the fact that the planes which the circles are going to be projected into aren't perfectly 90 degrees or parallel. So this is example 2. Let's move on to the features in Aberlink. So this is the model data. So we've measured a program from the CAD model to match the drawing that you've just seen. And relatively quick one, but you can see it's a similar setup. We have the datum letter is the circle which is projected into the front face. That is A and B. And as expected from the first example also, you'll see when it's all perfectly aligned and nominal, the concentricity is expected as is 0. So that is the back circle projected into that back face. 2 datum A gives us the 0 error. Now when we try to do the same on this, the nominal data, which has the tilted face, despite the fact that the through holes are perfectly aligned, because we're measuring this circle and it's having to fit the points into this angled face, the concentricity callout becomes 0.937. Now obviously that's not right, but the software is behaving as expected. It's trying to fit those points into the face, which is skewed, which is then skewing the position. Now the way around this is Aberlink has a function to construct a plane from a cylinder, which is what we've done here. And then you can construct a circle from the cylinder and plane intersection. And what this allows is it allows the circle to be true to itself because the projection plane is aligned with the bore. So if you really insist on using concentricity instead of runout or true position, you can construct a circle from the plane and cylinder. So just to highlight this in action, you would go plane, construct, double click your cylinder. So you've measured the bore as a cylinder prior to the construction. We hit the green tick and then we say circle construct where the cylinder and plane meet. This draws a circle, and then the callout is from the datum circle to the constructed circle, and you'll see we get the suspected nominal, as we know this CAD data is perfect with a 0 concentricity error. Now I can't promise that your parts will be like that, but you will find that that gives you a far more real world result versus the potential error from the skewing of the projection. So hopefully that gives you an idea of how to improve your readings. But yes, if you can measure the feature as a cylinder and then you can construct a plane and circle from that cylinder, the results will be far more true to themselves, and there won't be any weird skewing going on from any faces that are potentially not perfectly machined or square. Spindles and shafts are quite common for this, where they're held in a tailstock. The end faces have no relevance or function within the feature, so using planes to measure those circles into will always cause a bit of a skew, giving you incorrect concentricity readings. So that is example number 2.